Dear students, in our last video, we got introduced to circulations and how these circulations originate, at least at conceptual scale. And we learned that equators generally are the areas of low pressure, whereas the 30 degrees north and 30 degrees south, they are the areas of high pressure. And in upper atmosphere, that is around 8 to 10 kilometers above the surface, winds will blow from equator towards these high pressure belts and to fill the gap that is getting created here because of rising air that is resulting in this low pressure trough, the winds from 30 degrees south will or 30 degrees north will glide towards the equator, resulting in formation of trade winds. And this entire circulation happening around plus minus 30 degrees of equator is called as Hadley cell. Now, in addition to Hadley cell, there are two more cells that are important in the context of hydrology or which controls the global transportation of moisture. So one of them is polar cell and another one is mid latitude cell, and this is also known by the name of Farrell cell. So we'll look into details of this polar cell and Farrell cell, that how they form. Now we know that the insolation or the amount of sunlight that is received at poles is definitely much lesser than what is received at equator, and this is also less than what these 60 degrees north and 60 degrees south belt would get. As a result of which, the similar setup, that is low pressure gets developed here, high pressure gets developed at polar areas, and in upper atmosphere we get the same kind of circulation as we have in the case of equator to the 30 degrees north uh, of equator. But as you can imagine, the temperature difference or the energy difference here between H and L around the poles is weaker as compared to what we have around equator. But the kind of circulation that we see again is similar, that is in upper atmosphere. The wind blows from the direction of 60 degrees north towards the pole, and on the way they carry on the moisture, and then on to fill in this low pressure belt that gets developed here, the high pressure winds from poles blow along the surface, and their direction is decided by whether we are in northern hemisphere or in southern hemisphere, and because of Coriolis effect, they take a curve or a slight curvature as they move from the poles towards these 60 degrees north belt. And the circulation or cell that develops here is the polar cell. Now, another interesting thing that happens is at 30 degrees north is that when a so let us say that this is an equator. From equator we have this warm air parcels going up, then they travel towards these 30 degrees north belt, and when they descend back, part of it comes back towards the equator to fulfill this low pressure area, and part of it is diverted towards 60 degrees north, because there also we have a low pressure which is of comparatively weaker strength, but still it's a low pressure area, this is high pressure area, so some divergence of winds happen, and at 60 degrees north these winds also come here. And again we are also having the winds coming from polar region which are comparatively cooler, we meet at this low pressure area. So if this is our pole, let us say 90 degrees north, so wind is also blowing from here, and here we have a distinct temperature gradient. So here we would have relatively cooler air, here we will have relatively warmer air, and whenever this cooler air and warmer air meet with each other, it results in the creation of fronts. And fronts are very important as they guide the formation of cyclones, specifically extraterrestrial, or sorry, extra tropical cyclones, not terrestrial, extra tropical cyclones. Any cyclone formation that is happening outside the region of tropics. So when we talk about the tropics, we are essentially talking about the area between 30 degrees north and 30 degrees south. So as a result of which, what happens now, we learned that there is a circulation that is developing and we called it as a polar cell. There is a circulation developing from equator to 30 degrees which we call as the Hadley cell, and because of this polar and Hadley cell, which are essentially thermal in nature, because their formation is guided by the energy differences that we are getting from the sun, and different parts of the earth receiving different sun and as a different energy, as a result of which there is a vacuum of energy that gets created here, and the cell that originates here as a consequence of having a polar cell and Hadley cell is called as the mid-latitude cell or Ferrel cell. Now, all these cells they together constitute the general circulation patterns that we discussed in our last lecture, and they are very important for climatologists and hydrologists to learn about. Now that we are talking about these cells, let us also look into what happens that when these two fronts meet. So we learned that cool air is blowing somewhere and warm air is blowing somewhere, and whenever these two fronts meet, that results in the formation of wavy front, because you know that that things are not as stratified as we draw on pen and paper. So as this front forms a wave-like character, these winds, cold air and warm air winds, they get intertwined with each other, and because of Coriolis effect, they appear to be spinning in certain direction. And when we are talking about northern hemispheres or anything above the equator, the motion appears to be anti-clockwise. Whereas if you look this thing in south hemisphere, we will see that the rotation would be having direction of clockwise, and again this is because of the Coriolis effect. And that's why that whenever these 30 degrees, whenever this intersection of wind coming from 30 degrees and poles take place at the latitude band of 60 degrees, we get the origination of extratropical cyclone, which are essentially driven by meeting up of fronts. Also, another interesting thing that happens at the front is that whenever cold air and hot air they meet face to face, the hot air tends to rise up. Let us say this is our hot air front, this is our cold air front, which is coming from poles, and this hot air front is coming from equator. And you can imagine that this temperature would be higher as compared to the air that is coming from poles. So the hot air will try to rise on top of this cold air because of the difference in densities without intermixing into it, and this results into the formation of frontal or extratropical cyclones. Now this is what happens when we are outside the tropics, that is outside the 30 degrees north and 30 degrees south belt. But uh, we have to also look into what happens to the situation in tropics, how these cyclones get formed in Bay of Bengal or in Arabian Sea, because from hydrology and flooding perspective, they are important phenomena that keeps on striking India and its coast time and again. So the again the phenomena is same, that is when oceans get warmer, the warmer air tends to rise up. As it rises up, a low pressure trough is created. And when this low pressure trough is created, the air surrounding it, which is at relatively higher pressure, would run towards this lower pressure trough to occupy it. And now, because of rotation of the earth, these paths would be curved depending upon in which hemisphere we are in. So all these paths would appear to be curved when, because we are watching it from non-inertial frame and so on, as a consequence of which if we are in north hemisphere, these cyclones again would appear spinning anti-clockwise, which would mean that this direction which I have drawn by arrow, and whereas in southern hemisphere the picture will get reversed. But again it's the two troughs that are playing the role. And if we look at the pressure and precipitation distribution into these low pressure troughs, they would look like, that is we have a low pressure area exactly towards the center, and also this area, this band is going to also receive a fair share of precipitation. So if we on x-axis we plot the distance, and let us say on y-axis we plot the pressure, and we are measuring this pressure in millibars. And you can always look into conversion between millibars to atmosphere to pascals, standard conversions. And here we have wind speed in kilometer per hour. So we have an eye of a cyclone which typically spans a few kilometers in radius, and at this eye the pressure is lowest. So we have a low pressure here, and as we move away from the eye, this pressure increases gradually, and ultimately it reaches the atmospheric pressure, which is around 1000 millibar at a distance, considerable distance, depending upon what is the strength of this low pressure trough that is getting formed in the ocean. And most of these cyclones originate near the tropics or in the lower latitudes, exactly because of the reason that ocean water is relatively warmer around the equator because of the higher insolation that we receive in that belt, as we have spoken multiple times. Also, when we look at the wind speed also increases uh, as we go out, but just at the eye it is at the lowest, so it takes the form of a W. That means very it reaches the minima at the center of trough and then gradually increases and then it subsides. And that's why the impact of cyclones is felt for few tens to hundreds of kilometers whenever a cyclone makes a landfall. Similarly, if you look at the rainfall intensity, the eye has the maximum intensity of rainfall. We will represent this intensity of rainfall as I, which is centimeter per hour, because it will have a unit for a unit of rate, that is centimeter or inches per unit time, and typical unit that we would use is centimeter per hour. This is the distribution of pressure, and finally we have the distribution of wind speed. And in certain cyclones, depending upon its category, this wind speed could be as high as 160 to 170 kilometers. And cyclones are thus classified as category 1 to category 5, depending upon the wind speed that a cyclone would have. And the scale that we use to characterize this is called as Saffir-Simpson hurricane or cyclone scale to measure the intensities, and they form an important constituents of the transportation of moisture as well as high wind intensities whenever they enter into coastal areas, bringing lot of damages associated with them. Now we have learned these large scale features. As promised, we will look into the local or regional features into our next video. Thank you.